Hey everyone, welcome back to my YouTube channel. I am Xavier Smith. I've come back from the grave to make a video on related rates because it has been highly requested in my pre-calc class. So this may not be the best quality video. Clearly the lighting, I got a big shadow. But I really hope it will help. So I'm gonna go over what related rates are, go over like 3 easy problems, and then get into a harder problem, and then a pretty hard problem. Okay. So try to stick with me here. Comment anything down below if you need me to like make another video on this topic, do some more problems, or if you need me to make any videos on like pre-calc or stats, I'd be happy to. Okay, so first of all, related rates, what you're gonna do is, this will make sense later, you're gonna find a non-calculus equation, like an area, like an area equation, and then you are going to take the derivative in relation to time, because rate is like the movement something's going, like how fast something's traveling or being like filled up over time. So you're gonna get like something's being filled up at 3 inches a second or something. And then you're going to backfill with this equation after taking the derivative and solve, and a negative rate just means that distance is decreasing. Okay, so our first example, a radius of a circle is decreasing at 6 meters a second. How fast is area decreasing when the radius is 5 meters? Well, we know with a circle, our formula for area is pi r squared, because we were given like radius, so we need radius in this equation, and we need area, and we have area in this equation. So since we were just given area and radius, it is perfect. It is the perfect equation. So you just have to think back on your knowledge. It's a lot of geometry here. A lot of times it's just an area or like Pythagorean theorem, but we'll get into those later. Or like a volume equation. Okay, so now that we have our equation here, we are going to take the derivative in relation to time. So the derivative of a in relation to time is just dA over dt, the derivative of a in relation to the derivative of time, like in relation to time. Okay, equals, now we're going to take the derivative of like r squared, well, pi r squared, which we bring this 2 down, it'll be 2 pi r, so 2 pi r, right? But then we just took the derivative of this in relation to time. So we have to put, okay, we got 2 pi r, but now we just took the derivative of r in relation to time. So now we have 3 variables here, and it looks like we were given 2 to solve, so now we have a 1 variable equation. Super simple, we just plug things in. All right, and you don't really have to keep these units, just throw them on in the end. If it says like how fast is the area decreasing, well, that's probably gonna be like inches squared or something. It'll be something squared per like second. Okay, so now we need to solve for how fast the area is decreasing when the radius is 5 meters. So this is what we're solving for. The area, the change in area over change in time. Okay, so dA over dt equals 2 pi times our radius is 5, and then dr over dt would be -6 because it's decreasing at 6 meters a second, so -6. Okay, so I'm not going to simplify any of this with like my calculator or anything. I just know that this is 10 pi, and then 10 pi times -6 would be -60 pi. So dA over dt equals -60 pi. And then for like the measurement here, we see we're in meters, and we're given meters per second. And since it's area, I'm going to say meters squared per second. So now this is our equation. dA over dt equals -60 pi meters squared per second. That is how fast our area is decreasing. Okay, if that makes sense, you can try this next one on your own, or you can watch me do it again. Okay, so the area of a square is increasing at 40 centimeters squared per second. Okay, so what rate are the sides that should probably be, what rate are the sides increasing? Sorry. Increasing. When a side measures 3 centimeters. Okay, so here again we have area, side, so we are probably just using the area formula for a square, which usually it's like a rectangle is length times width, but the thing is, in a square, the length and width are the same, so it's really like length times length, which is side times side, which is side squared. Okay, so for a square, we have A equals S squared, where S is like a side length. Okay, now we have to take the derivative in relation to time. So dA over dt equals, this will be 2s, and we just took the derivative of s in relation to time. So we have to say ds over dt. And this is our equation. Okay, what are we solving for? What rate are the sides increasing? So this is like the rate the sides are increasing in relation to time. Okay, so we're solving for this here. Okay, so dA over dt, the rate that the area is increasing, is given to us at 40 centimeters squared per second. So just 40 equals 2 times, a side is 3 centimeters, ds over dt. This simplifies to 6, and then we're just going to say ds over dt equals, divide both sides by 6, you get 40 over 6, and you could simplify that to 20 over 3 if you want to. And again, this is the rate the sides are increasing at, so they're not going to be in centimeters squared. A side is measured in just centimeters, so centimeters per second. So they are going to be increasing at 40 over 6 centimeters per second, or 20 over 3 centimeters per second. Okay, now a lot more difficult one, actually, but I think you'll have it. You can try it yourself if you want to, or I'll do it right now. Okay, 2 boats leave port at 12 p.m. Boat A travels north at 25 miles an hour. Boat B travels west at 15 miles an hour. At what rate are they separating at 3 p.m.? Okay, so here we have one of these like coordinate things, which I really don't like, but it's simple because we were just given north and west. Those are easy, but if we were given like north 30 degrees, that'd be a bigger problem that I don't want to solve right now. So we're just going to say, okay, so boat A is traveling north, right? So this up here is north, and it's 25 miles an hour, so just throw 25 miles an hour, and that is boat A. Okay, cool. Now boat B is traveling west at 15 miles an hour. So this is boat B, and it's going at 15 miles an hour, right? B. And it says, at what rate are they separating at 3 p.m.? Okay, so the rate they're separating is this distance between them, because this hypotenuse is giving the distance between the 2 boats. So it's just saying, at what rate is this hypotenuse like expanding, right? So what rate are they separating, which is just how fast the hypotenuse is expanding. Okay, and then this is a right angle right here because we are given like north and west, which makes a 90-degree angle. Okay, so what equation could we use here? We are really solving for this hypotenuse here, and we have a right triangle. So I'm going to say Pythagorean theorem, which you know as a squared plus b squared equals c squared. But I'm actually just going to use x, y, and z to make it easier because this is our x-axis, this is our y, and then this will just be our z. Okay, so we have x squared plus y squared equals z squared. Okay, cool. Now what do we do once we have an equation? Well, we take the derivative in relation to time. So this will be 2x dx over dt, because like the derivative of x squared is 2x, and we took it in relation to time, so you got to throw in the dx over dt, of course. And then that's the same thing with y over here. You'll do 2y dx over dt. And don't get tripped out that usually when we take, usually we take derivatives in relation to x. So if we took this derivative, like whenever there's a y and you take a derivative, you're like, oh, I got to throw a y prime or a dy over dx over there. But now we're taking in relation to like time.
So none of this is time, so we always have to put like dx over dt. That's supposed to be a y. dy over dt. I don't know if that made sense, but hopefully you got what I was picking. Well, I don't know. Got what I was putting down. Okay, and then we will have 2z dz over dt, right? And actually, we don't need any of these 2's. They can cancel. Okay, now we have x dx over dt, y dy over dt, and z dz over dt. Well, clearly we have like dx over dt, 15 miles an hour, and we have dy over dt, 25 miles an hour. But how do we get x and y? Well, we were given another thing in our equation here. At 12 p.m. they left, and at 3 p.m., like what rate are they separating? So they've been going for 3 hours. Okay, well, if they've been going the constant rate at 25 miles an hour for 3 hours, like this Y guy has, the boat A, then we're just going to say 25 miles an hour times 3 hours is 75 miles. I hope I did that math right. So 75 miles. Now, boat B was going 15 miles an hour for 3 hours, which would be 45 miles. And again, if like boat A started at like 1 p.m., boat B started at 12 p.m., it'd be different. So just be sure you look at the problem and interpret it correctly. Okay, so now we have an x, a y, a dx over dt, and a dy over dt, but now we still have 2 missing variables, z and dz over dt, and we are solving for dz over dt. So that must mean there has to be a way to get z. This problem isn't impossible. So again, if we go back to the Pythagorean theorem, we can solve for z by using 75 and 45 by plugging it in here. X squared plus y squared equals z squared. So this will be 75 squared, I put it in order, that's y squared, plus 45 squared equals z squared. And I'm not going to simplify that. I'm just going to say z equals the root 75 squared plus 45 squared. All right, so that is our z value. Now we have everything we need, and I'm not going to simplify anything just because I don't have a calculator and I can't do it in my head. Okay, so now first, x is 45. Dx over dt is 15. Plus y is 75. And dy over dt is 25 miles an hour. Equals, I'm going to have to write this on the side, 75, the root of 75 squared plus 45 squared dz over dt. And then we just divide by 75 squared, like the root of 75 squared plus 45, which would be dz over dt equals, like how fast they're separating, is 45 times 15 plus 75 times 25 over the root of 75 squared plus 45 squared. And then they're separating at miles per hour. So miles per hour. All right. Well, you can simplify that in your calculator and get whatever you need. But honestly, you don't have to simplify it. You got the right answer. Now, where did my water go? Oh, it's right there. Not sponsored. I wish I was sponsored. That would be nice. I don't make any money on this. That's why I don't make videos anymore. It's kind of annoying to make videos when you don't make money. It's like, sometimes it's not worth it. I mean, I like teaching people, but sometimes it's just not worth it. It's not worth it for my time. Okay, so now 2 final examples. Gas is filling a sphere at a rate of 250 inches cubed per second. How fast is the radius increasing when the radius is 3 inches? Okay, so this one is a little weird. We have volume, and if you didn't know volume from filling the sphere, you got inches cubed, which is not area. Area is like a squared value. Oh, dang it. Area is a squared value, and volume is a cubed volume thing. So this is V equals 4/3 pi r cubed, I believe. Correct me if I'm wrong. And actually, don't correct me if I'm wrong. I don't want to know if I'm wrong. Okay, so we're solving for volume. Again, we have volume here. Like, we're given volume, so we need volume in the equation. And we're given the radius. And that's in the equation as well. All right, so this equation covers all the bases that we have. let's keep going. Okay, so again, take derivative in relation to time. dv over dt equals, this 4/3 pi is the coefficient, so we're going to multiply by this 3 using the power rule. So it'll be 4 pi r squared times, we just took the derivative of the radius in relation to the derivative of the time, so it'll be dr over dt. Okay, now let's see if we can plug in. Well, we have dv over dt, how fast the volume is being filled up over time, which is 250. So let's just say 250 here equals 4 pi, and then are we given the radius? We're given the radius is 3 inches. So this is 3 squared, and then we're solving for how fast is the radius increasing, which this is the increase of the radius over time. So dr over dt. Great. Right? And I'm just going to simplify this. This is 9. 9 times 4 is 36. So that's 36 pi, right? And to solve for dr over dt, I just divide by 36 pi on both sides. So I have dr over dt equals 250 divided by 36 pi. And then what will this be in? How fast is the radius increasing? So that's probably just in inches, and we're doing inches per second. So I'm just going to say inches per second. Again, if you tried to keep like these measurements, like inches cubed and stuff, you're going to get so thrown off. Like it's not even going to be funny. Right now, what we're doing is pretty simple, but I can imagine in the future it gets a lot more complicated. And you might actually have to keep these numbers, like this inches cubed, and it's going to look ugly. So right now, when you have the chance, just don't keep the measurements. Just don't keep them. Okay, finally, the hard problem. All right, this is one that will stump a lot of people. Try it if you dare. Okay, a 10-foot ladder leans against a wall. If the bottom is pulled away at 2 feet per second, what is the rate at which the top of the ladder is sliding down the wall when the ladder bottom is 5 feet from the base of the building? Wow, that's a lot, right? Okay, so here's our little diagram here. There is a ladder, a 10-foot ladder, leaning against a wall, right? The wall is y feet high, and the ladder is x feet away. Again, we're given that x is 5 feet from the base of the building, so I'm just going to throw that in, x equals 5, and we're given that this is 2 feet per second, and then are we given anything else? So we're trying to find like how fast the ladder is sliding down the wall, which would be dy over dt, right? Like the distance, the rate traveled in the y over like in relation to time. Okay, so we're solving for dy over dt, but we don't have y either. But something to note here is we do have a 5, and like we do have 2 parts of a right triangle, so we can solve for y in the future. Important to note. Okay, again, if we're solving for really anything on a right triangle, we're going to use Pythag, which would be here x squared plus y squared equals z squared. So let's put that down. Okay, and then again, take derivative, 2x dx over dt plus 2y dy over dt, that does not look like a y, equals 2z dz over dt. And again, these 2's cancel because there are 2's on everything. It won't matter if you keep the 2's, you'll get the same answer. It's just like, I don't want to do the work, if you understand me. You know, I just don't want to do it. So I just take the 2's out immediately. Okay, so we have x is 5. We're solving for dy over dt. Let's check. We can only solve for one variable in this equation, so we need everything else satisfied. Okay, we have x, which is 5. So we'll start plugging that in. X is 5. Dx over dt, how fast is like the x moving? How the ladder is being pulled away at 2 feet a second. So dx over dt is 2. Then we need y, which we can solve for y right now, which would be 5 squared plus y squared equals 100. Well, 10 squared is 100. So this will be y squared equals 75, and y would just equal root 75 here. Okay, plus root 75 times, we're solving for dy over dt, right? And we're given z is 10, and then this is another thing. You're like, we have another variable here, dz over dt. How do we solve for that, right? And then if you think, you're like, hey, this ladder's 10 feet tall, right? This hypotenuse here isn't like moving. It's not like the boats that are moving apart from each other and the hypotenuse is getting bigger or smaller, right? The ladder's not expanding or contracting, which technically some ladders can do. They can go up and down. But we're going to say this is just a flat ladder, right? It cannot change its length. Well, this ladder is not changing its length, right? It has to stay the same length. It's just physically impossible for this 10-foot ladder to just grow or shrink. So it is not moving over time. The distance increased or decreased in the size of the ladder does not move over time. So that value, dz over dt, is 0. So just think through them and be like, is this set object, is the height of this ladder ever changing? No, it's always 10 feet. So that distance, dz over dt, the rate of change in the size of this ladder over time is 0. Again, I just wanted to hone that point down because this is a different type of question here. Okay, now solve for dy over dt. This will be 10 plus the root 75 dy over dt. That looks like an x. Dy over dt equals 0. 10 times 0 is 0. Don't just say, well, since that's 0, I'm just going to get it out and just put z on the other side. No, z is multiplied by that. Make it 0. Trust me, I did it wrong the first time as well. But just trust me. Okay, so this will be root 75 times dy over dt equals, move this 10 over, negative 10 dy. Why do I draw x's? Dy over dt equals negative 10 over root 75. And then what is this measured in? It's measured in feet per second. It's moving away at feet per second. Okay, so here we are given that, again, negative means it's going down. The distance is decreasing, which is good. So we know it's sliding down the wall at 10 over 70 over root 75 feet per second. Okay, I hope someone stayed through this whole video. It's a doozy, but I hope this helped you in pre-calc. I hope this helped everyone asking. Leave any comments down below. If you need me to talk about another math subject, I'd be happy to. Just wish I got paid. You know how it is. Money motivated. And then please subscribe, I guess. I guess I'm coming back to this channel. So, might be named Xavier Smith Tutoring soon. Okay, well, I'll see you guys in the next one. Thanks for watching.